Alright guys, welcome to AST from Mr. C's house. So we're going to hang out with me today. I'm going to start this off by saying, excuse the noise. There are 5 people in my house since there's no school for my kids, so you will hear them in the background. So I'm going to do my best to isolate that. Plus I think there's a dishwasher going. But anyway, the point is we're going to go through engine performance today. That's what we got going on right here. Welcome to engine performance. This is my favorite topic on the car. And there's a duality in this word performance. So from the get-go, let's address this. When we say engine performance and we're talking about in the car, we're really talking about how well the engine is running, not how fast the car is. But that being said, every time we have class together, I'm going to tell you what I know about performance. So we're going to talk about performance as far as the engine is concerned and how to make more. And then when we get to steering and suspension, I'm going to teach you guys what I know about performance there and brakes and on and on and on. So as far as today goes, today we're going to do some very rudimentary, what I like to call a glossary. Let's make sure we're on the same page. In reality, this should be the last class that you take, but they have you guys take it first. It's not up to me. I would have you take engine repair, which is the mechanical side of the engine first, but that's not how they set the school up. So today we're going to talk, and I'm going to show you pictures, and I have a PowerPoint and all that. And then what is nice about this is I'm going to edit in some clips of me going outside, and I have some cars in the driveway right now. So forgive my terrible editing skills, they're not great. And I might get sidetracked, but you guys bear with me and we'll get through this together. Since we're at my house, let me take you through my garage here. We got my work table over here. Sorry, the floor is squeaky because it's sealed. I don't know if you can see that, and it's a little wet. And I got a Miata. This is perfect for today. This Miata has a misfire, so I'll show you guys what's going on with it. Air, spark, and fuel. There's my bikes. I play a bass solo for you, but we're supposed to be talking about engine repair. Over here on the table, this spark plug here has this crack in it, so I believe that's my culprit right here. I got new ones coming, so we'll find out when they get here. So I'd like to start this class with this video of an R35 engine being hand built by Nissan Techs. We're in engine performance, and I just think this is cool. Plus, the dude who builds it gets to put his name on the front of it, which that's awesome. So if you don't know, the R35 GTR is a V6 that powers the newest Skyline R35 GTR. And look at this dude wearing gloves. It sounds like a hospital too. This is a nice engine stand. Man, let me get one of those things. That's nice. Is he bored to death because he does the same thing every day? He didn't look real enthused. I would be very excited to be doing this. There's so much money right there he's holding. Can y'all hear I have an 11-year-old playing Fortnite. I'm sure y'all can hear him celebrating upstairs. I guess this is a torque wrench also. Beep. Little. Man, this would be a sweet job for like 2 or 3 weeks until then it would become monotonous, but man, this is a fancy seal installer. This is cool. That's the easiest, best way to do that. When you work for the factory at the dealer, you get access to these kind of tools. Alright, watch him miss. Oh, he hit his thumb. Not really, but. Oh, yes, these are pistons, yes, yep. Oh, they all have rings, very good. How many? 6 of them? He's totally faking this for the video, too. This is a sweet tool as well. This is like the coolest piston ring compressor I've ever seen. We have a piston ring compressor. It's a generic one, and you guys will use it when we work on those engines outside. And when you watch how easily, boop, his goes in, and then when you fight with ours, you'll be like, man, that's a nice tool. And this guy's got some sort of hydraulic operation going on. That's pretty sweet. Those heads are aluminum, but they are very heavy. And when you're leaning over the fender of the car trying to put one on, it's awfully heavy, so A little bit of Earl everywhere. Alright, who knows what that part is? I know you can't talk back to me, but let's pretend like you can. What about those? What do we call those? I normally wear one. It's beeping like that? It'd be so funny if it flatlined. Oh, the engine's dead. Look at how many chains this bad boy has. Because it is a V6, we've got no less than 3. There's probably one more for the oil pump. Oh, what are we doing? Playing violin? So this is a technique. Well, this is a clearance check, and I'm going to have you guys do this. This is called a valve adjustment. And so when we get to engine repair, I'm going to have you guys do this too. There are fewer and fewer engines that still require that, but it's a good skill for you guys to have. And since we can do it in the shop, we're going to. Look at this lift too, man. So before they let it go, they're going to test it. So this is him bringing it to the testing room. We're going to kind of quasi hook it up to intake, exhaust, coolant, and the oil is self-contained. Look at him fake pointing, like he's just doing that for the video. Yeah, this one says 620, and that one says... If you look, there you go. Look at that turbo getting hot. Ooh, son. You guys want to roast some marshmallows? So this is a special thing that these engines are still hand built. There's not a lot of these left in the world. Koenigsegg, Bugatti, the big expensive brands, not big, but the very expensive exotic brands still do. But for this to be a Nissan engine, you know they build Sentras, right? Like, they build absolute garbage sometimes. Hand built by this dude. That would be cool if I could put my name on a engine one day, but... Alright, so the next thing we need to address is as we're moving into this new module, engine performance. I've got CDX pulled up. I need you guys to look here. There's engine performance and there's engine repair. There's engine performance and there's engine repair. We are not doing engine repair. We are doing engine performance. Please don't spend the next month doing the wrong homework. So I need you to click on AST 8 engine performance. The course ID 44AE3F. When you enter it, it'll show that I'm your instructor right here. And then what I wanted to show you guys was right here if you click announcements, I've added the syllabus for you, which is what I would normally hand to you first thing this morning. If you click this, it will download a Word document. You're welcome to print it, but I've given it to you now. And then here's the worksheet that I normally would hand out, which is what the video is mostly going to show. So you can follow along if you want. Either way, I gave it to you there, so that should be helpful. Alright, so we're back on the worksheet here, guys. On page 1, if I hadn't already said it, your homework is due April 25th at midnight, which is a Saturday 4 weeks from now. This vocabulary first page, I'm going to go over in this PowerPoint. So I would very much like for you to write down, take notes. It is helpful if you read it, write it, and hear it. So we're going to start with... Oh, it doesn't work quite like that when I do it, huh? Let's do that. Alright, so we need to start with torque. You need to understand both what it is and the equation on how we figure it out. So we'll describe torque as a twisting force, and I want you to think the tool in your toolbox is a torque wrench, and what do you do with it? Well, you twist a fastener, a nut, a bolt, or whatever. So what we're describing is how hard you're twisting it, and this is important that you understand. This is how much force we're applying. This has nothing to do with how quickly you applied that force. Does that make sense when I say that? So, and this is the exact same torque that when we talk about, hey man, I just put a bunch of performance parts on my Mustang and I took it to the dyno and got some new numbers. I have a horsepower number of X and a torque number of Y. That torque is this same torque. And this is the beginning of one of my favorite arguments a lot of people don't understand. And so I would pose to you now, if we were in class, I would ask you guys, if we took these two numbers, torque and horsepower, from the dyno, and you guys know what I mean when I say that, we took it to a dynamometer where they measured how much power the car is making at the rear wheels. So if you asked your grandpa with his Chevelle, like, what's the difference? The old generation would tell you in simple terms, torque is the force that pushes you back in the chair, and horsepower is that top end. And I'm going to explain why that's not true at all. And here's a great example. When you guys are in class, we have the CDL class on campus, and there's an 18-wheeler in the parking lot. So we've got an 18-wheeler. And let's pretend this morning I rode my bike. That 18-wheeler makes tons of torque. I'm talking like 800 foot-pounds of torque. My motorcycle at peak RPM makes maybe 40 foot-pounds of torque. Now, that being said, who's going to win in a race? And you already know that there's no way that 18-wheeler is going to catch me on my bike. So torque is important, and we need to know what it is and what it means. But that's not necessarily acceleration. That has very little to do with acceleration, to be honest. So on this page, torque is a twisting force. The engine itself is making rotational energy, right? So if you're not familiar with how pistons travel up and down, I'm going to show you when we're back in class. I've got some pictures here in a second. But the basic idea is that the pistons go up and down and they're attached to this crankshaft, and it creates a rotational direction at the crankshaft. And we're going to use that rotational energy from the engine back through the transmission if we have a transfer case, through the drive shafts if we have them, to the differential, to the axles, to the wheels, right? It's all rotational from the engine back. So we want to measure how much twisting force this engine is making, and that's torque. And we measured in foot-pounds here in America. So it would be 1 foot. And the easiest way to think of this is if I gave you a fastener, a nut, a bolt, or whatever, and it was mounted horizontally, and then I gave you a 1 foot long wrench, and you hung this wrench on the fastener. Okay? So let's pretend the wrench is sticking out straight like your arm. Stick it out straight, and then we're going to put, at 1 foot, we're going to put 10 pounds of weight. So now we've created 10 foot-pounds of torque. If that makes sense. It ought to. If it doesn't, this is why you guys are going to call me later. Take notes. That's another thing. Y'all should be taking notes of what I go over that you can't ask me because we're not in class. So after this lecture, I want you to either call me Thursday night or Friday night, and each one of you needs to call me or I'm not going to give you attendance for the day. And then we'll have just a 5-minute conversation about what you learned and questions you have, and then what we need to go into further. So torque is force times distance, force at the end of the wrench, and how long the wrench is. And we all know that if I took a short ratchet versus a really long ratchet, it's a lot easier to get those fasteners off with a really long ratchet. And that's because the equation is simple, force and distance. I can only make so much force, but I can change the distance I'm putting on this thing by getting a longer ratchet or wrench. And then the formula for torque is increased. This is fun because you know that the transmission is a bunch of gear ratios. And so in this idea, force and distance, the distance is those gear ratios. By the time we get to the rear tires on something like a Mustang, the torque at the tire is almost 5,000 foot-pounds because of torque multiplication. And we're going to go over that a lot in manual transmissions, but I just think that's cool. We don't normally measure that. We normally measure torque at the engine, and then we do horsepower at the rear wheels. But either way, what I need you guys to understand the difference. It doesn't matter how long it takes you to do this rotational force. It's just the rotational force. So then we move on from torque to horsepower, which is the one we really care about. Horsepower is that work, that rotational force that we did, times time. Okay, so I told you it doesn't matter how long it takes you to tighten that fastener with torque, but with horsepower, that's that number, torque, times a time signature that we have on the engine, and the one that we use is RPM. RPM stands for revolutions per minute. So it doesn't matter how much work we're doing for torque or how quickly we do it for torque, but in horsepower that's the difference. And then you always see these two numbers together when you get a dyno sheet, torque and horsepower, because if we look at the equation at the bottom here, horsepower is equal to torque times RPM. So I can't figure out what the horsepower is unless I know what the torque is as well. So that makes better sense and kind of enlightening you. So let's go back to our example with the motorcycle and the 18-wheeler. My motorcycle at, alright, y'all write this down or just imagine this in your brain, at 12,000 RPM. Do you understand how high that is? How high does your car rev outside? Do you ever pay attention? Most V8s don't go more than 5 or 6,000 RPM, so my bike goes to 12,000 RPM. And at peak horsepower makes about 100 horsepower. About 100 horsepower. I told you about 40 foot-pounds of torque, but because we're taking that torque number here, this bottom torque number, and multiplying it by this RPM, the RPM is a huge number, so that helps it build our horsepower. But it only makes that horsepower at the high end of the RPM range. So let's talk about the 18-wheeler. The 18-wheeler makes like 800 foot-pounds of torque. And the rev limiter on an 18-wheeler is less than 2,000 RPM. My motorcycle idles at 2,000 RPM, but it's the same equation. Torque times RPM. And thus, the horsepower number on the 18-wheeler will be 4 or 500 horsepower. And I want you to just think about this for a moment. Motorcycle, 40 foot-pounds of torque, 100 horsepower. And then the opposite for the 18-wheeler. 800 foot-pounds of torque, 400 horsepower. And this helps explain which one will be faster. The bike will always be faster because the horsepower is faster. It's a better example would be, let's pretend we've got a bodybuilder and then a really skinny guy. And I ask them both to pick up a jug of milk. Well, they can both pick up this jug of milk. They can do that much work. When I say work, we're talking about torque. They can both do that much work. Now I ask them to pick up a pallet full of bricks. The strong man can do it. He has more torque. He can do that work. The skinny guy can't pick it up. Well, he can't accomplish as much work, regardless of how quickly either of them do it. So on my motorcycle, it weighs absolutely nothing, right? And then, alright, I'm kind of a fatty. But anyway, with my big self on it and a full tank of gas, we weigh maybe 500 pounds. So it doesn't require a lot of work to get that 500 pounds moving. Let's talk about that 18-wheeler, and let's pretend it has a trailer full of whatever. So now that we've got a 50,000 pound trailer and then a 10,000 pound truck, I need to be able to do a lot more work. So torque is work. Horsepower is how quickly it gets that work done. So we take those numbers and we look at it. The 18-wheeler does a lot of work. And it can do more work than what we need. If we took the trailer off of that 18-wheeler, it still wouldn't beat my bike. It can do a lot of work. Maybe I don't need you to do that much work. Maybe I would rather trade the ability to do less work on a light vehicle for more horsepower. That means it could do it quicker, more quickly. That's a better way to say that. So let's talk about a big heavy muscle car. Well, yeah, it required a lot of torque to get that big heavy muscle car moving. Those cars weigh 4 or 5,000 pounds. We've got a Miata. The thing doesn't weigh anything. It really doesn't take a lot of horsepower or a lot of torque. It doesn't take a lot of work to get this thing moving. In both cases, though, if we took two identical cars, nothing was different except for the horsepower and torque. The one with higher horsepower will always win. Now, we could do some crazy examples here, but the fact that torque is part of the equation for horsepower, they'll never be really far apart. But I just think that's interesting. So, when we talk about acceleration, that has nothing to do with torque. Acceleration has to do with the gear ratios in the transmission, how your suspension is set up. So, these two numbers are one of those things that when you're a very young white belt, it's important that you have a big torque and horsepower number and that, it's bragging rights. Oh man, my car makes. But that doesn't tell us much about the acceleration, the deceleration, or the turning, which is what a race car does. And if it's just the peak number, that doesn't tell us that we make a lot of horsepower over the RPM range. So, let me draw you an example here of what I mean when I say this RPM range. So let's just draw here and here. So this would be how much horsepower I'm actually gonna make. I'm not good at drawing with a mouse, y'all, so leave me alone. And this would be, oh, I did that backwards. I want RPM over here. You're out of here. RPM over here. RPM over here, and then how much power it actually makes, right? So my bike revs really, really high. So we're going to start at like 2,000, and then as I rev higher, I'm going to make horsepower. So going this way, this is how much horsepower, right? So I make like no horsepower, no horsepower, no horsepower until I really get in the RPM range, okay? I only have this little usable section of RPM. I have to get to like 8,000 RPM before the bike actually starts to pull, which is different if let's do a Mustang. A Mustang might only rev like this far, 5,000 RPM. So he goes more like this. Not gonna rev nearly as high, but starts to build this horsepower. I should have done more of a like this. Starts to build horsepower much, much faster. We're going, and so he's got this usable range now of RPM. And that's important when we start shifting gears and we start doing things. So things to think about. Here's a picture of a cylinder block. We're going to use these words. I need you to understand what they mean when I say them. So here's a cylinder block. This is a V8. It's got a hole on the back over here for the starter. The camshaft would go through here. This is an all push-rod engine. So each one of these black holes would be the cylinders, and there's another set on this side. So that orientation we would call a V, and there are 8 of them, so it's a V8. Please note these other holes, and if we were in the classroom I would show you outside, but there's other holes. So I'm going to ask you now, haha, you didn't know this was coming. There's going to be 2 questions in this video, I think, to prove that you watched it. So question 1 is, what are those little holes for? Not the big ones, those are the cylinders, but what are the little holes for? And this is a thought-provoking question. I just want you guys to, normally we have dialogue. So the combustion chamber, when I say that, what I'm talking about is this red area. When the piston comes to the very top of the cylinder, it's not going to hit anything because that would be a problem. And then this line from, if you can see my mouse here, this line here is 2 separate pieces. The bottom is the block that we just saw, and the top is the cylinder head, which I'll show you in a moment. So these are 2 pieces that we bolt together. So this area here, this combustion chamber, is a lot like your lap. I like to say that. Sit down, you have a lap. Stand up, you don't have one. So if we took the cylinder head off, there is no combustion chamber. It's not a tangible piece. You can't go to parts and order a combustion chamber, and so therefore I literally can't show it to you outside of a drawing. But this area, this red area, when I say that, this is what we're talking about. However much room is in here. Some older engines are designed that when this valve opens, this guy here, if he was all the way open out to here, he would never touch this piston. Newer engines, though, this combustion chamber is so tight, which makes better efficiency and better power, that this valve might touch the piston. So we call that an interference engine. And this is why you absolutely need to do your timing belt. Anyway, so sorry for the duplicate slide. A compression ratio. The compression ratio means how much travel that piston has gone and how many times we've compressed it. You guys know what ratios mean. So at the very bottom dead center, the piston's all the way at the bottom. We fill that area full of air and fuel, and then when the piston goes all the way to the top, how much have we compressed it? How many times? The standard for most vehicles in the parking lot is 10 to 1. We're going to have a discussion about octane later. That's another myth. A lot of people do not understand octane. So octane is only when you have a very high compression ratio, and we'll talk more about that later. So the stoichiometric value, you have to commit this one to memory. Please write it down, highlight it, take notes of this. The stoichiometric value is boring and you don't care. However, it's 100% essential to making sure the engine's running right. And this only works with gasoline. It's not the same for diesel. It's a different number. And it's not the same for E85 ethanol. It's a different number. But for all the passenger vehicles in the parking lot that run off of regular unleaded gasoline, the ideal air to fuel, right here, air to fuel ratio is 14.7 to 1. Write that down, remember it. Some people call it lambda. You might see that on the scan tool. You might just see the AF ratio, which is what we're aiming for. So you know that the car has O2 sensors, and what they're doing is trying to monitor the exhaust to tell the computer we're either at 14.7 to 1 or we need to be, and therefore the engine computer can make adjustments and aim for this. So 14.7 is perfect. That's what we're aiming for. If I was running lean, which is what we say when there's more air than there is fuel, okay, then this air number would be higher. So a lean condition would be something like 17 to 1, which would be a bad thing. Um, this is the part where I would ask you what's more dangerous, running lean or running rich. And in your most people say running rich because you think, oh, gasoline could explode, it would be bad. That's not really how gasoline works. The problem with when it runs rich is that we're not actually burning all the fuel. There's not enough oxygen, and we know that the atmosphere is not pure oxygen. The atmosphere is like 78% nitrogen, which is why those nitrogen tires are a rip-off. Anyway, so we're talking about atmosphere here, just air, not O2. But if it was like 12 to 1, that would be a rich condition where there's too much fuel and not enough air, and it simply won't burn that fuel. But if we run lean, something 18 to 1, then instead of burn, combustion, you've heard this word, instead of a slow controlled burn, which is what combustion means, then we have this other word you've heard, detonation. Detonation, like a bomb? Yes, that's what I mean. So when engines blow up, it's because they ran lean. Back in the day, you had a carburetor and no computer, and you ran the RPM all the way to the roof, and the fuel system could not keep up. And as it asked for more and more air and fuel, we have more than enough air. The atmosphere is not going to run out of air, but your fuel delivery system ran out of fuel, and then the engine blew up. That's why as it ran lean. That is also why every car in the parking lot now has a rev limiter, because it's engineered from the factory that I cannot supply enough fuel if we exceed this RPM. So anyway, 14.71, say it. Tell your friend, tell your girlfriend, your boyfriend, tell your dog right now, 14.71, commit it to memory. Alright, stroke and bore. This isn't as relevant on today's vehicles, but if you're into muscle cars, you will have heard these terms. Stroke is how far the piston travels up and down. Bore is the diameter of the cylinder across. So, if we're going to determine the engine's displacement, which I'm going to talk about that a little bit more in a second, we are going to talk about bore and stroke. But when you think about this, if the piston goes a large distance of stroke, so from the bottom all the way to the top, if it travels something like, hold your hands out and hold 6 inches of distance, okay? If it travels 6 inches, that's a long stroke. And then an F1 engine has a very, very small stroke, so hold your hands 2 inches apart, okay? So the difference in a big stroke and a little stroke. Now, this is absolutely paramount when we talk about performance. Long stroke builds lots of torque, and then we know torque is important for horsepower. So all of this inline 6 cylinders, I want you to think about all the big trucks, the 18 wheelers are inline 6s with a turbo. All the Cummins engines are 6 cylinders, inline 6 with a turbo. If you're into JDM cars or European cars, the Supra, the R34, and previous GTRs, a lot of the BMWs were all inline 6s because they're phenomenal for torque. At the cost of the problem with the long stroke is you don't get very high RPM. And I can explain this simply. If I gave you a rope and tied it to a bucket and I told you to throw it this way and then turn around and snatch it and throw it the opposite direction, it would put a lot of stress on your arm and that rope every time it changed direction. If it has a long stroke, it builds a lot of inertia, and it's very difficult to stop it and turn it around and throw it the other way. So if you think about the piston going up and down and up and down and up and down, that's kind of what we're working with. So generally speaking, if we have a long stroke, we do not rev very high. Again, all the 18 wheelers, they don't rev very high. The Cummins engines don't rev very high. The Supra never rev very high. All those Nissans, the BMW don't rev very high. However, at the trade-off of a big torque. And then bore is, what we used to do is you would take the cylinder and drill the cylinder out wider and increase the bore. And anytime you can add air and fuel, you make more power. Anytime you add air and fuel, you get more power. So if the cylinder's bigger, you get more air and fuel, you make more power. The danger here is if we drill so much that we compromise the integrity, the strength of the engine. So I took a break right here. Let's go outside and look at my little car show we have going on here. And that's a crawfish my friend made me. We have security, of course, Leonardo, and the alien. He's holding it down. Alright, I want to take a minute to talk about displacement. So let's pretend this terrible drawing that I did here. is the engine from the side. So this is a 4-cylinder, 1, 2, 3, 4. I got our cylinders up and down. Slapped a cylinder head across the top to show you. And at the bottom here, let's pretend this is as far down as the piston travels. And all of this cylinder up until it meets the cylinder head. And we know this black area here would be our combustion chamber. But anyway, if we wanted to figure out the displacement of an engine, we would do it this way. We would put the piston in bottom dead center, and let's pretend we took some fluid, some whatever you like, Dr. Pepper, and we filled this cylinder all the way to the top. And this one, and this one, and this one. So now we have displaced a volume of area. And let's take all of that liquid and pour it into a measuring cup over here. Now, if this was a 2-liter 4-cylinder, and we did this, we filled each cylinder up. When we poured this fluid into the measuring cup, it would measure 2 liters. That's where these numbers come from. The displacement is from bottom dead center, the entire cylinder, times however many cylinders we have. Alright, let's go outside and look. Here is the inline 4-cylinder on my motorcycle. If we look, here's the cylinder head, and that is the cylinder, or the cylinder block itself. And we see that it is a 650cc engine, which would be 0.65 liters. Here we have my son's itty bitty dirt bike, cylinder head, cylinder itself, and both, well, this one is a 1-cylinder, and it's 110 cc's. That would be 0.11 liters. Over here on this Miata, we have 4 cylinders, and it measures in at 1.8 liters, which would be 1800 cc's. Alright, now we're going to move on to this next part of the worksheet, the 4 strokes of an internal combustion engine. So, outside in the parking lot, all the consumer vehicles are 4 strokes. 4 strokes. All your chainsaws, some of your dirt bikes or weed eater will be 2 strokes, and I will talk about 2 strokes on week 3 or 4, as long as they're rotaries, because I want you to understand how they work. But everything we work on outside, the diesels also are these same 4 strokes, and they are as follows: intake, compression, power, exhaust. I'm going to draw them for you in a moment. We're going to really dig into this, but for right now, just write down, remember. And we always start with intake when we explain it. So when you hear me say it, this would be the way you hear everybody else say it. When you take Nissan, Honda, Chevrolet, Ferrari training at the factory, it will be in this order. And when you explain it to your grandchildren, do us this favor and do it this way. So our 4 strokes are as follows. I wanted you guys to see a long block. If you hear these words, short block and long block, a long block means just about the entire engine. So if we were going to build it from the bottom up, it would have the cylinder block itself with a head on it. It would have all the valves, camshafts, crankshaft, pistons, rings, connecting rods, oil pan, valve cover. You see on here, there is no exhaust manifold and there is no intake manifold. So this would be a complete engine ready to put in the car minus the manifolds. If we get a short block, that's everything I just said from the head gasket down. So not to include anything in the cylinder head up. So just one of those things, this is important. If you accidentally drive through water and blow the engine up, or whatever reason we need to replace the engine, the example goes like this. At Toyota, they quit offering short blocks. So in order to replace all the parts, one at a time, in a V6 Tacoma engine, the 2GR, would cost, just in parts alone, $35,000. Whereas, if we go to Chevrolet and ask them for a short block for the world famous, we'll use LS, the V8, the 350, they'll sell you that short block as an assembly for like $8,000 because it's already put together. It's easier, it goes in faster, and we can save a lot of money. So you will hear these terms, short and long block. They're referring to this. The easiest way, and I remember when I was a young man, long block is everything but the manifolds. A short block is everything I just said from the cylinder head down. So not to include the cylinder head. Here, if you've never seen one, we have a piston, this top piece. You'll notice the rings on it, please. We'll talk about that. It has a wrist pin holding it to the connecting rod here. At the bottom, this is hard for you to see. There's bearings in here, and when I say bearings, you always think of like a ball bearing. That's not what we're talking about. It's a half moon, and we'll have you guys take those engines apart. We'll look at them, and then the bottom is called a cap. So because this is the main, well, how do we call this? The main seals go on the crankshaft, and this is connected to the crankshaft. So these are called main caps and main bearings, not cam caps or cam bearings. But either way, here we have a crankshaft. Please note the common line through the center. We have to have somewhere to bolt it to the engine as this whole elliptical thing rotates. So there will always be a common line. And then, so that would be here, here. These is where the main caps would go. And then you'll notice here, and it's hard to see, but this one is closer to you, and this one is further away from you. They're all different, and the reason is this is a 4-cylinder, 1, 2, 3, 4, and I do not want all 4 cylinders doing the same thing at the same time, right? So this one is 180 from that one, this one is 180 from that one, and the firing order on this one might be something like, who's going first? If you go first, then you go next. So 3, 4, 2, 1, or however. But you'll notice that we do that on purpose. Then we have the cylinder block. We've already looked at one of these. This one is a straight 6 big holes. 1, 2, 3, 4, 5, 6 are my cylinders. They're in line, so straight. Again, here are these little holes. I want you guys to tell me what those are for. On the side, if you've ever heard the word freeze plug, that's what these are. A long time ago, we were worried that if the water froze and expanded, it would put a hole, because it would too. It would crack the cylinder block. So instead, what we did was put these freeze plugs. They're light aluminum. This way, it would push the freeze plug out. This is a very old engine to still have this. You won't find these on your modern engines. Further, Further, we have camshafts. They're easy to tell the difference between a camshaft and a crankshaft. I know in the very beginning they sound so similar. Camshafts have lobes. These are lobes, lobe. And the crankshaft has no lobes. The crankshaft has these offset portions where the connecting rods will be attached to. But the camshafts are different. Again, you will note a common line through. This is where we're going to put the main, well, not the main, we're going to put the cam caps with bearings to hold these guys. And then these lobes are what's going to push on the valves and open the valves in whatever configuration, push rod, roller cam, mechanical, whatever. These lobes are what's going to actually open the valves so I can get air in and get air out. And then here's the bottom of the cylinder head. I like to keep this head on the table in the classroom to show you. If this is looking at the bottom of it, my valves would go here where my mouse is. This whole side would be intake. This whole side would be exhaust. And then again, you'll note those same small holes, like what we saw in the block, are in the head too. So this might be a big clue on why we would have these holes there. Then, now that we're done with that, I would normally do this on the whiteboard at school, but we're just going to have to do it like this. So we're going to do our 4 strokes of the internal combustion gasoline engine. So this will work for diesel, sort of, but not really. Only minus 1 step, but not a 2-stroke and not a rotary. But anyway, anytime you ever see it, it will go in this order. And those of you who are following along saw me write, or saw that it was written, intake, compression, who's next, what? Power, and exhaust. So, what we're going to do is draw the piston. So the piston is at the bottom, and it comes up, and then it goes down, and it comes up. Every time it travels a distance from the bottom to the top, that's called a stroke. That's why we call this the 4 strokes. So I'm not going to draw a piston, I'm going to draw an arrow. And the arrow will indicate whether the piston was going from the bottom to the top or from the top to the bottom. So in the intake stroke, I need to pull air and fuel into the cylinder. And the way that I do that is I make the piston travels down and it creates a vacuum, and that vacuum pulls air and fuel into the cylinder. And then guys, this is the easiest way to remember it. We always start on intake when we explain this, and if you can remember that intake goes down because I'm creating a vacuum to pull air and fuel in, then you know what the rest are. If I'm already down, I can't go down again, right? So therefore I must go up, and if I'm already up, then which way am I going? Right, so this is pretty simple. This is the easiest way to remember this. Please take note of this, guys. I am going to make you draw this for me, this exact same way when we meet in class. This is super important that you understand this. So on my intake stroke, my pistons will go down. That will, or whatever, I should know this. This is not a 4-cylinder, right? This is not 4 separate cylinders. Let's pretend this is 1 cylinder going through the 4 strokes of the 4-stroke process. So this will work on a 2-cylinder, this will work on a 3, 5, 8, 10, 12 cylinder. It doesn't matter how many cylinders we have. If it's a 4-stroke engine, each cylinder and each piston go through these 4 strokes to complete one cycle. Okay, does that make sense? If it doesn't, write this down. I'll show it to you. I'll prove it to you on the engines outside, so take notes of this. Alright, so on intake, we come down, pull air and fuel in. Compression, I'm going to make the piston go up, and that's going to squeeze the air and the fuel. And when we squeeze the air and the fuel, it's going to become volatile. Then, right here in the center, so not during a stroke, I cannot draw with it. Anyway, my spark plug is going to fire. So we have air and fuel, we squeezed it, the spark plug will fire right here. Now that air and fuel is going to burn, and this is a power stroke because the burn, oh, let's do some cool here. I know what to do. Watch this. Let's get a nice little red color here. We'll even get an airbrush. I'm on fire. Alright. So now the air and fuel is going to burn. That burning and expansion will push the piston down. That's our power stroke. Now that the piston is down and burned all of its air and fuel, we need to get that burned exhaust out. So in the exhaust stroke, the piston comes out up and it pushes the exhaust out. So now what we're going to do, I'm going to change it up here, and we're going to draw valves. We'll do blue for intake and red for exhaust. And when I have you draw it, remember this. This will help me tell if you guys were paying attention. The valves, intake valves, we will draw on the left, and this is the same valve. This is the same cylinder, right? So the intake valve will be on the left side, exhaust valve will be on the right side. And then open or closed mean, and then this is how we draw it. So let's pretend this square up here is the top of the cylinder. A closed valve looks like this. An open valve looks like this, because the camshaft has pushed it away from the cylinder head, and then now we can have air and fuel or exhaust go by. If this is hard for you to conceptualize visually, I have one on the table at school. I would love to show it to you. Remind me next time we're in class. So either way, let's go do our intake valves first. We'll do blue on the, I did not hit that. We'll do blue on the intake stroke. I obviously need the intake valve to be open. When it opens and the piston travels down, we're going to pull air and fuel in. Then, when I compress the air and fuel, I don't want that valve open. It would just leave, and then I can't compress it. When we burn it, spark plug fires, and we hit a power stroke, if this valve is open, then instead of doing work and pushing the piston down, it'll just leave out of the intake. Also, if you have a bad, nasty backfire, that could be your timing is off and it's going up the intake instead of out the exhaust. And then over here, exhaust stroke, I really don't want that exhaust now, this burned, we burned it here in the power stroke, now it's spent air and fuel. I don't want that to go back in the intake, I want it to go out the exhaust. So that's our intake stroke, and we'll do red for exhaust. Over here, I do not want you open on the intake stroke. I don't want to pull exhaust in, I want to pull fresh air and fuel in. When I go to compress it, I don't want anybody open. Don't do that, it would leave. I want to squeeze it, compress it. On the power stroke, I don't want anybody open. Don't leave. I need that burning to push this piston down. And then finally, when I get to the exhaust stroke, that's when I'll open this exhaust valve. Okay? Now, we just went over a lot, and this is, I'm going to help you in the way that it helped me. Intake, compression, power, exhaust. On the intake valve, the piston moves down. If you can remember that, you know which way the piston is going across the other three, right? Over here. The intake valve was only open on one stroke, right? Closed on all of them except for the one stroke, and they called it the intake stroke. Oh my goodness, right? That should be easy to remember. And the same thing for the exhaust. It's only open on one stroke, and they call it the exhaust stroke. Imagine that. So that's how I remember it. Hopefully that will help you guys remember it that way. Commit this to memory. We are going to go over this. Moving on to page 3. Let's talk about engine codes and body codes. So what we like to do is reuse the same engines. If we talk about, we're going to use Toyota because that's the one I'm familiar with. We have a 4-cylinder, and we're going to name it a 2AR. And all that means is that this engine, we're going to call it a 2AR. It'll be the same engine no matter what car we put it in. And that being said, it is 100% true. You can get a 2AR in a Corolla, a Camry, a RAV4, the new CHV thing, and the small Lexus. If we talk about a Chevrolet, the world famous LS, you could get a LS. It's the same V8 in the Tahoe, the Silverado, the Corvette, the Escalade. It doesn't matter. We're going to reuse the same engine to save money and make things work better. So engine codes mean this is that family of engine. If I say B18, that's a world famous Honda engine. The Chevrolet example would be an LS. A rotary, a 22B would be a world famous example of that. So I want you guys to understand the difference between body codes and engine codes, because this vocabulary will help you stand out and then start to establish yourself as young technicians. And then body codes work the exact same way. So if I said to you a DC9, what that translates to in Honda speak is that's an Acura Integra of the year between this and that. So we will do that as well. You've seen, what's a popular one? If you guys are into trucks, like the K9 Blazer, I think that's correct. And that means that make and model between these years, or that platform. So what I've got, this I like to do this in person, but we're not in person, is I've got, oh no, if you guys can see the side over here, that's not going to work. See if I can hide that, yeah. Alright, so I've got a little PowerPoint, and this is what we do, is I tell you the name. So if I say DC9 like I just did, and then you guys guess, is that an engine or a body code? And this is just something to lighten the mood. But the point of this, I want you to go to work and start paying attention. As you become proficient in your brand, Lena, you're at Volkswagen, right? And Zach and Peyton, forgive me, I can't remember what you guys said. Wherever you're at though, we're going to reuse these engines. And once you've put a water pump on that engine, so let's use my Toyota example. If I put a water pump on a Corolla with a 2AR engine, when I go to do a water pump on the RAV4, it's the exact same bolts, parts, procedure, and so it will do you a big service to start learning them, since we are becoming the expert here. The other thing too is that you guys are quick lane in the beginning. If you know exactly how much oil goes in a, let's use my wife's Highlander, so she has a 2GR, and that 2GR comes in the Highlander, the 4Runner, there's an option for the RAV4 and the Camry. It also comes in the Tacoma, if I didn't say that already. Oh, no. But it's the same engine, so it uses the same oil filter and gets the same amount of oil. And if you can see the engine and go, oh, I know, then that saves you time. You don't have to go look at the book. You don't have to pull it up on the computer and those things. So there's, 2 reasons why I bring this up. But anyway, let's play. So RB26DETT. And there's a clue on this when the TT stands for something. Is it a car or is it an engine? It's an engine. And the TT stands for twin turbos, which is cool. Let's do R32. And there's some more letters I left off, but R32 is actually the car that engine came out of. So earlier we looked at a video for the R35 GTR. This is the generation 3 before it, right? 32, 33, 34, and 35. So that's what that means when we say that. 2JZ, everybody ought to know, well, because I'm a Toyota guy, jeez. And the T right here stands for turbo. So this was the super engine. As far as GTE and Toyota, that meant general, so this is emissions. And then this one has a turbo, so a T in there. My wife's 2GR has a FE, and that means federal emissions, which means America. Just whatever extra stuff that you guys don't really need. But EK9, anybody know? This is one of my favorites. Civic Type R, love it. MX5. You guys see these on the road. I know you've seen this one. Oh, I gave it away. Damn it. Miata. That was one on my driveway. Imagine that. C7 Z06. That part right there should help Z06. Anybody? Corvette. And then you guys just saw that we're up to C8, the new one, which is mid-engine rear-wheel drive. That's cool. It also looks really good. EJ25. Is that car engine? It is an engine. In fact, we have one of these on the table in the lab. So if you guys want to see it disassembled, this is what's in the Subarus. It's a flat engine, which is interesting. So if we look on the left side, that's the cylinder head here. And then here's another one over here. So it's not a V engine. It's flat. It's opposed. The crankshaft is in the center. And I have two pistons that go this way and two that go that way. It's interesting. There's a lot of Porsche engines this way. The benefit to this is if we look at how tall from the bottom to the top, this engine is very short. So you do that in a car that you want to be low to the ground. So the FRS 86 BRZ has this engine. A lot of the Porsches do this. If you're into bikes, the Honda Goldwing does this. Anyway, LS9 is the world famous Chevrolet V8, the 350. N55. I looked this one up. I didn't know this one, but I needed something to stump you guys. This is a BMW engine. Look how weird this is. All the pulleys over here on one side. I don't know a whole lot about European engines, but that's interesting. Inline 6 with a turbo, you can't beat it. MT10. No, this is not a socket. It's a motorcycle, tricked you. Ha ha ha. I think it looks really cool. Look at those headlights. Doesn't it look like a robot? Anyway. 911 922 is a Porsche. And this is, I have some beef with you, Porsche. I thought you said it's a 911. So 911 in this case means that's the model. So if I said a Miata, that's the model. And then the 922 on this one is the actual body code. So that would be like if we did the Integra DC8, DC7, DC9. Those are all different Integras, but different family generations. When we did the, what else did we look at? We looked at that Corvette. So I showed you a C7 Corvette, but the generation before that was a C6, on and on and on. So the way that they do the 911s, which is the model, Corvette model, the family and the body code is this other number, this 922. So you could tell somebody, I have a 911 944. I thought you said it was a 911. It is, but it's a 933. Alright guys, find this part of your worksheet. Let's move on to the next part. The three things it takes to make an internal gasoline combustion engine are as follows. Write them down. Air, fuel, and spark. You heard me say at the beginning of the video with this Mazda. Anytime you have an engine that doesn't run or has a misfire, it takes three things to make this engine run. Air, fuel, and spark. And so the way that you go down your diagnostic branch is, I need to prove if it has fuel, I need to prove if it has spark, and let's talk about air. I've never really seen one not have air, if that makes sense. So since I was going outside, I'll show you guys. Look, I hit a tree and then my son smashed the handlebars. Yeah, we messed those handlebars up. Anyway, so here we've got this Miata. So air, it's always going to have air. Like, even if you disconnected the air right there, head and then exhaust out, even if you disconnected the intake, it'd still get air through the throttle body, so it's never air. So we're looking for why this engine doesn't run. There's the injector rail, but I always start with spark. Spark is the easiest to prove. So you see I've got spark. This one has spark plug wires and spark plug. If you want to prove that it has spark, it's as easy as pull the coil off or pull the spark plug wire off. Go grab your spark plug. And of course this one is broken, but the point is, all you have to do is stick it back in either the coil or the spark plug wire. Now don't hold it by hand because it might shock you, but go get something insulated or put it like this and have your friend turn the engine over. And when you watch it, it should be a bright blue. You should be able to see it like lightning. And then there are the fuel rails. If you are not if you had spark and that wasn't the problem, then you could go look, do I have fuel? If you don't have fuel, you could go down that branch. Alright, back to the worksheet. So, for three things: air, fuel, and spark. Any engine, it doesn't matter if it's two-stroke or four-stroke, we need these three things to make an engine run. So your weed eater, your lawnmower, your chainsaw, your dirt bike, your car, it doesn't matter, your helicopter, we have to have these three things. It's always fuel and spark. Spark is the easiest to check. Then go check, make sure you have fuel. It'd be one of those two. So I have this question: during the four-stroke cycle, when does the spark plug fire? Right? One, two, three, four. On which one of these strokes does the spark plug fire? And it's a trick question because it fires right here, boop, in between intake, compression, power, exhaust, in between compression and exhaust. Compression and power, forgive me, even I make mistakes. So anyway, right here in between 2 and 3 is when it actually fires. And then the timing to the cam and crank is important. We accomplish this with. So I have a couple of things to say about this. What makes these pistons go up and down is the crankshaft, and what makes the valves open on top is the camshafts. And if I have a valve open when I don't want it to, let's pretend right here, remember on this stroke nobody opened? What if it did open and that piston and valve touched each other? Or over here, we want the exhaust valve open to push exhaust out. What if it stayed open too long and they touched each other? Then we'd be rebuilding the engine. So these are very important, cam to crank. And then one of the things I like to talk about is every time this guy goes all the way down and all the way back up, this crankshaft down here makes a complete circle, right? So it's one full rotation. And then we know we have to do it again. So across one cycle, one four-stroke cycle, the crankshaft spins twice. However, up here, I only want this intake valve to open on this one stroke. So if this camshaft rotates at the same time this crankshaft rotates, it would open here and open here, and that's not going to work. So for every full cycle, the crankshaft will rotate twice, but the camshaft will only rotate once. And this is important when we go into engine mechanical and you're listening to noises, because if you didn't know this, the bottom half of the engine, that's supposed to be an A, the bottom half of the engine rotates twice as quickly as the top, and that might help you diagnose a noise. Like, let's listen to this knocking noise, and then you put your stethoscope on it, and hold on, man, we're at 800 RPM or 1200 RPM, which is revolutions per minute of this crankshaft, but it's not nearly as fast as I hear the engine going. Oh, then there's something on the top, if that makes sense. And then let's go back to our worksheet here. So what I like to do is go over the evolution of camshafts, but before I do that, the following section is for you to take notes. VTEC and VVT, I write this down, are variable timing events. So when the intake and exhaust valve actually open and close, we control with the computer now. And you say, why? Why don't we just make it mechanical? Because if I can hold those valves open longer or open them further, I can get more air and fuel in and more air and fuel out. And in this way, I can make more power and make the engine more efficient. So a long time ago in a galaxy far away, you'd have a hot rod, and you'd say we put a fat cam in it. And when you put a fat cam in it, it goes wah ba da ba ba da ba ba da ba ba da ba. It makes that cool sound at idle. And this made a lot more horsepower. But at idle, it was running way too rich. It was nearly stalling out, and that's not what we want. We want the best of both worlds. So at idle, when you're not in the RPM, you're not asking for very much power, the engine can be super efficient and we can achieve those high miles per gallon numbers. Or the customer steps into the throttle and now we need power. Well, the computer says, alright, I'll hold everything open a little bit longer, get some more air and fuel in and out, and now I can make more power and I can boast. Now we're going to go sell the car, right? This is what it is shipping units. Now I can sell the car and it gets great miles per gallon, and I can brag about how it has great horsepower, torque numbers, acceleration numbers, whatever we want. So now let's talk about the evolution of camshafts over time. So we're going to start with a very basic example here with the old V. So this would be an old push rod, V8 Chevrolet 350, something simple. And the way that we look at this from the side is this is where our pistons are going to go up and down right here. So the crankshaft would live here. Okay, crankshaft, push rod, piston. Yes, you follow me? But how do we get these valves to open and close, right? We got intake and exhaust valve. How do we get those to open and close? We need a camshaft. On a push rod engine, you would put the camshaft right here in the block. And we put like a chain or a belt or some gears. Terrible drawing. And then push rods, which would come up like this through the head, a rocker arm, and that in this way, when this lobe pushed the push rod, it would open this valve. So this was great, but in order to have enough lobes, so when we looked at the camshaft, to have enough lobes to open these valves, the best I could get away with was one intake valve and one exhaust valve. And the intake valve is always bigger, always, 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 than the exhaust valve, no matter what engine you ever look at. And that, look how much dead space we have in the cylinder that we're not using. So you don't hardly ever see this anymore. We're moving away. Just about every engine has moved away from this. But if you hear the word pushrod engine, that's what this means. So then we went to, you may have seen this. Oh man, my handwriting is even worse. Single over. Oh, I can't even spell it right. Anyway, let's use the, where's the text? Your text right here. Check this out. If that works better. Single overhead cam. You may have seen that. So what we did is we got clever. So this is, we'll just use the inline 4-cylinder because this is when you saw this and this is the easiest way to do it. Easiest way to do it. So crankshaft bolted to the bottom of the cylinder block, just like over here. Nothing different. Connecting rod, piston. Alright, so how do we get these valves to open and close? Well, what we'll do is instead of the camshaft being here in the block, is we'll put a camshaft here so that it is directly touching these valves. We'll put a chain or a belt around it like this. In this way, because we've spread it out, we can achieve 2 intake valves and 1 little exhaust valve. Boop. And then you guys know the spark plug lives like right there. Spark plug lives right in the middle there. So now we have less dead space and we're getting way more air and fuel in. This is a good thing. Also, look at the length of this push rod. This would take time to translate motion and it would limit our upper RPM. Whereas this one, if the camshaft is directly touching, opening and closing these valves, we can go a lot faster, have higher RPM. So you saw this in your 1980s and 90s Japanese inline 4-cylinders is kind of where, and on the side of a Civic is where you saw SOHC, single overhead cam, and then I can't make this any simpler. The pushrod engine, where's the cam? It's in the block. Single overhead cam, where's the camshaft? It's over the cylinder head. Where is it? It's one, single. He's not good with the ladies. It's a single. He stayed single forever. That was terrible, I'm sorry. And we put it over the head. And then the other one that you may have seen on the side of the Civic, double overhead cam. So what we're going to do now is have, hey, draw. Why are you not drawing? Oh yeah. What we're going to do now is put 2 camshafts, double, there over the head, and now this dude can hit just the intake valves, and this dude over here can hit just exhaust valves, and I can get, God, my drawing is so terrible. We can get 4 valves per cylinder. And so when we compare all the, oh, check this out, I have the fill button, boop, didn't work like I wanted to. That one didn't either, and of course that one didn't. But if we look at the difference between the dead space all in here that we're not using, much less here, so way more air and fuel. And then this is what we use on just about every engine in the parking lot is going to have this configuration over here. Everybody's moved to this double overhead for this reason. So just like the other 2 crankshaft down here, but this one has 2 camshafts and a chain or a belt holding it. So this is what we're going to have. The one on the table at school is this way. The ones we work on are either single or double overhead, but you're hard pressed to find this older style push rod engine. So I wanted to put that in there. Now let's move on to page 4. Different colors of exhaust smoke can indicate these things. Now I need you to write this down. Regular exhaust smoke is a gray color. If the engine is running rich, so it has way too much fuel and it's not burning it, that extra gasoline will come out as exhaust smoke that is very, very, very black. Very, very, very black. Or soot. Okay, so write this down. Colors of exhaust, black equals the engine is running too rich. If the exhaust looks a little blue, and this is hard to imagine, but when you see it, you go, well, I'll be damned that it is blue. When the exhaust is blue, that means it's burning oil. So some way oil is getting into the combustion chamber and burning with the oil, the air and the fuel, which it's not supposed to. Finally, if we have white exhaust smoke, that is not exhaust smoke, that is steam. So somehow we know we have water, right? Because we need to cool the engine off. Just like we know we have oil, we need to lubricate this thing. If we get water into the combustion chamber, it'll come out of the exhaust as white. So the engine's not running well. We're talking about engine performance. The engine's not running well, and the exhaust doesn't look right. Well, what color is it? What do you mean what color is this exhaust? No, no, no. Is it gray? That's normal. Is it black? That's rich. Is it blue? That's oil. Is it white? That's water. Compression and compression ratio. We went over compression ratio. Let me go back to my drawing here. Compression. So when this piston goes all the way to the top here, we know that he has rings on him. So if the rings are worn out, these rings right here, if the rings are worn out, the air and fuel will go past the rings and get down here, and that'll create a situation where we have low compression. If these valves are worn out, then when I go to squeeze this, I won't get high compression. So it's like a health check. You go to the doctor and he wants to check your vitals. One thing that we will do is a compression test on an engine. It's easier if I just show you and I have my gauges. I'll bring them. We'll do this. That's kind of the last resort. This engine isn't running well. Does it have air? Of course. Does it have fuel? The fuel pressure gauge says it has plenty of fuel. Does it have spark? I can see the spark plugs firing. Well, why is it not running well? Well, it's got low compression. So this isn't something that will fail overnight. A spark plug will fail, right? A coil is an electrical component, it'll fail. The fuel pump is an electrical component, it will fail. Compression is something that slowly gets worse over time. So this would be an old, tired engine. Yeah, it's my dad's 86 Monte Carlo, if they even made those in 86, I don't know. And it's got 400,000 miles on it, and it's running rough. We're going to start air, fuel, and spark, but we find all those are good. Hey man, why don't we run a compression test? Oh, look, it has low compression. So actually the Miata in my driveway, one of its big problems is I did a compression test on it, and let's go back to my drawing here. When you do a compression test, you're going to do all the cylinders one at a time to try to figure out which one it is, or perhaps there's more than one of them that are having problems, right? So, oh, those are text. Let me just delete that. Delete. This is actually probably faster than the whiteboard if I can learn how to do it neatly. There we go. Alright, so when I did this Miata, we got four, let's just use texting. We've got 4 cylinders, 2, 3, and 4. And when I ran a compression test, the book says I should have 180 psi of compression. That's what I found on cylinder 1. And the engine has 280,000 miles on it, so you can't be mad at it. It's not like it's new. We get to cylinder 2 though, and I only have 105 psi of compression. Cylinder 3 has about 120, and then cylinder 4 has 160. So if we said from the book, it should have something like 180. Okay, let's pretend that we're doing one in your driveway, and you're asking me, hey man, what do you think about this engine? Well, 180 is perfect, so cylinder 1 looks good. 160 is really not that far from 180 given the age and the miles on this engine. Now, if the engine had 30,000 miles on it, that's way too much. Something's not right. But if it's got 100,000 miles or more, and it's not that's really not that far from perfect. I'm really not worried about it. That's not going to cause a problem. 120 is way too far different from what it's supposed to be. So something's not right here. 105, of course, is just about half of what I want. So, and then really, in reality, because this is a 4-cylinder, so imagine my cylinder head across my 4-cylinder. Yeah, why are you not drawing? Because I'm not drawing. Alright, so let's pretend these are my 4 cylinders, and I've got my cylinder head here with a gasket. So we'll do my cylinder head, which you guys remember has valves and camshafts and stuff. And there's a gasket that lives. Let's do the gasket a different color. We have options. Do the gasket in red. The head gasket lives here. Gotta have a nice gasket. And then my 4 cylinders down here. I'll just draw it like this, nice and simple. Okay, guys? 4 cylinders. Boop. So, really, what has probably happened is this engine has overheated, and aluminum does not like to get hot. So, what I'm suspecting is that across these 4 cylinders, this one looks great, that one looks great. It's probably not a mechanical failure in the cylinder. Probably this head got warped and is beginning to lift. Now, I'm drawing it in a very over the top way. When you look at it, it obviously is going to be a giant curve like this, but it's probably warped across these 2 cylinders here. And that compression, instead of going where it's supposed to go, is probably bleeding into the neighboring cylinder. And the fact that you find 2 of them next to each other that are very low is indicative of this. If they were all 160, I'd be like, that's not that bad, because I have a piston in here, and he's got 1,000,000 miles on him, and I know those rings are wore out. Those rings right there, they're wore out. If the customer was really worried about it, we could rebuild the engine. If all 4 of these cylinders had a number like this, 105, that means that these rings and pistons are wore slap out, right? If it's even across all 4, we got to think of it that way. But in this one, we found just these 2, so that's where we're leaning. So anyway, that was a little example about compression. Compression ratio is how much you squeeze it. Hydraulic and mechanical lifters. We used to use mechanical lifters. They still have a valve adjustment. I want to show you this in the lab. This is a service you want to sell if it's available. So if it has mechanical lifters, every 60,000 miles or whatever the book says, we're going to try to sell them. Hey man, you need a valve adjustment. But if they're hydraulic lifters, they adjust themselves hydraulically, which is cool. The lubrication system on the car. This is important for you guys because what you're touching right now, lube tags, oil, drain plug, oil filter, oil pump, and that's it. There will be a gauge or a dummy light in the vehicle because if the oil pressure gets low, what happens when we have 2 pieces of metal that are very hot rubbing on each other? They'll melt together. So this is important. This is like the most vital thing, this lubrication system, but it's really simple. Cooling system. We went over this when I was telling you guys about when to open the radiator cap. So hopefully this is not new, but it's very simple. We know we need coolant, right? We've got to have something to exchange thermal energy. To move it around, we'll have a water pump. To keep it in the engine or in the radiator and then allow it to move, we'll have a thermostat. We're going to have hoses, the actual heat exchanger itself, the radiator, and a fan on the radiator, plus the cap if the pressure gets too high to allow the coolant to leave. So the difference between a compression test and a cylinder leak down test, hopefully guys we will be in class together on week 4, which is normally when I do this, and I'd much prefer to show you in person, okay? So if it gets to where we're still doing this the next week or 3, then I'll do a video of the difference between the 2, but I'd really much rather show you in person. So write that down, remind me later. A loss of engine compression. Now, this is question number 2. What all can you think of would cause a loss of compression? And it could be, you can make up any situation you want where it's 1 cylinder or all cylinders, but I want you to think, if you need to look at the cross section of an engine, where we're actually squeezing the air and fuel. If it can leak out of any of those spots, this is where I want you to write these down. I'm gonna ask you about this when we talk. What can you think of? And this is just some big brain stuff we're kind of looking at. So, day one review questions at the bottom of the worksheet. Which one of these strokes is not one of the four strokes? And combustion is the correct answer. We are getting combustion on the power stroke, but when we talk about it's intake, compression, power, exhaust. So, trying to trick you there. All of these following components are located internally to the cylinder block except for which? And the answer there is the camshafts. The camshafts should be over the head unless we're working on a really old engine. However, in my 13 years of dealership life, I've never had to work on a pushrod engine. And to be fair, I've never had to work on a distributor or a carburetor. Now, we have a carburetor in the shop and I want you guys to work on it. I'm going to show you how a very simple carburetor works because I want you to be able to fix your lawnmower and your weed eater. And like every spring, like this time of year, you go for a walk in the neighborhood and there's a lawnmower at the side of the road and you're like, hey man, can I have this lawnmower? And they go, no, you don't want it, it doesn't run. And you're going to go, well, with about $3 worth of carburetor cleaner, it's going to run. And then I'll turn around and sell it for 20 bucks. It's the same problem on every single carburetor, and I'll show it to you. We'll talk about it. But anyway, keep moving. Number 3, both a B18 and B16 may be found in the same vehicle, and that is true. They can both be found in an Integra or a Civic. To make an internal combustion gasoline engine run, we need everything except we don't actually need a battery. And if you want proof of this, go pull the starter on your lawnmower and it'll start without a battery. So once the engine is running, the alternator on our cars, once the engine is running, the alternator is producing its own electricity, which is awesome. And then it can power itself. This is why you can push start a manual car, and this is part of why if you jump start a car, it doesn't immediately die, it keeps running, is we don't actually need that battery to make an engine run. Now, if you were going to try to pull start your, let's pretend you have a big V8 in your car and you're going to try to pull start, it'd be basically impossible. But, you know, during the four-stroke cycle, when does air and fuel burn? And it burns on the power stroke. The amount of air and fuel that is pulled into the combustion chamber depends on the length of which stroke, and that's the intake stroke, and by the lift and duration of which valve, and that's the intake valve. One of these timing components is superior in terms of durability, and that's the timing chain. Timing belts, of course, will snap, and then if the piston and valves touch, we're rebuilding the engine. However, timing chains can be noisy, so you might see some luxury brands still putting timing belts in the engine, which is excellent for us. We want to do that because at 90,000 miles, when the book says, customer, you need to replace the timing belt, that's a 5 or 6 hour job for us. That's easy money that we want. However, a lot of engines have moved to timing chains, so we don't get to do that anymore. One of these rolling assemblies helps reduce friction, and that'll be the hydraulic lifters. And again, I'll show you guys the difference when we get back. Excuse that yawn. Of the two components, which timing setup comes with guides, and that's the chain. And again, I'll show you guys. I've never met a belt with guides, but all timing chains have guides. And this is important here. I did this on purpose. The chain will never wear out. The chain will last forever. But those plastic guides will not. So if you've got an engine with a timing chain, 150,000 miles, those guides are probably slap wore out. And you might get away with selling a customer new guides. And if we're going to do that, we're going to do new guides, new chain, and a tension all at once. So if you can get 5 or 6 hours, that's where it's at. Oil is used for all of the following, except rust prevention. The aluminum cylinder head and the aluminum cylinder block don't rust, so there's no rust prevention. But that was a thought-provoking question. Oil is used to lubricate, obviously, but if you didn't realize this, oil is also used to cool the engine, and oil is used as a hydraulic fluid all over it. Alright, I told you earlier what's the answer to blue exhaust smoke. That means we're burning which one? The engine is overheating. What is not the cause? Could it be the water pump? If the water pump fails, will the engine overheat? Absolutely. If the thermostat gets stuck open or closed, will the engine overheat? Absolutely. If the cooling fan fails, will the engine overheat? Absolutely. If the temperature gauge fails, will the engine overheat? No, that's not really how that works. A compression test will yield accurate results if the timing is off. And the answer is no, it will not, because timing is when do my valves open. And if you're trying to test the compression and the valves are not opening when they're supposed to, or they're opening when they're not supposed to, or on and on and on, then you're not going to have good results. And it's even more true for the cylinder leak down test, which again we will go over either more thoroughly. I'll have a video, or we'll do it in person. I'd much rather do it in person. If I change my exhaust, I must compensate the fuel because the engine will run rich or lean. So I've got new exhaust, which normally means bigger exhaust. So am I getting more air or more fuel? I'm getting more fuel, right? No. No. Gotcha. I'm getting more air. More air is able to leave the cylinders. And I must compensate with more fuel because if I don't, all that extra air, the engine will run lean. And I put this on here. Nobody ever thinks about this. The first thing you should buy to put performance on your car is software to change the computer. Okay? It's very easy to put a cold air intake on. Now we have way more air. It's very easy to put exhaust on. Now we have way more air. But the computer doesn't know to tell the injectors to spray more fuel. And then it runs lean. And then it detonates. So step one, if any of you ask me, hey Mr. C, I want to build a race car. What's the first part I should buy for my Civic, my Mustang, my Challenger? It doesn't matter what it is. My answer will always be, you need to find whatever the solution is for air to fuel on your car. So on my Subaru, I'm very fortunate. The Cobb access port is a little module that I can buy, and it will tell the computer to change the air fuel ratio. And it's not very expensive. Otherwise, you're looking at aftermarket computers to handle that. But in any case, I always run with that first. So that brings us to the end of the worksheet. On my lecture for the day, I normally like to go over the PCV, but we're going to do intake and next week and exhaust the next week, so we'll do that. Exhaust week 3 is my favorite because that includes forced induction, which is like the best thing ever. That is absolutely my favorite lecture. So this ran a little bit longer than I wanted it to. If you guys have questions, you've got my number. Text me. I expect you to watch this sometime Thursday. Friday, I will call each of you in the afternoon. I'd rather you call me first, and we're going to talk for just 5 minutes. Just then I know you're on task, following along. I had a couple people not get their CDX done for the last module, and that's never happened to me before. And I have kind of a reputation at school for having nobody's ever failed in my class. So I'm gonna keep up with you guys because I cannot have you guys failing because of CDX. So a little bit of that too. So anyway, um, you got my number. Call me. Otherwise, I will talk to you Friday. That'll be good.